Hello, you crazy math nerds! It's the big crazy math nerd, Kitty Morgan, back for another fun video. So let me talk a little bit about one of the big things of calculus. It's this weird word called derivatives. And we're going to get there, but we got to kind of take you back to the day and bring you forward into the calculus. So let's talk a little bit about the picture right here. I have a picture of just a normal parabola. And I've drawn some things that people have asked you to do over the years, these lines that help you find the average rate of change. Woo, there's no line thing now. Oh, I'm going crazy today. Hold on just a minute. All right, so for example, the guy I have here in red, he is a line that connects -2, 4 to 1, 1. So we say that this line right here, because it is kind of going through the graph, is called a secant line. It is called a secant line. Let me write that up here for you. I put it in red since we're doing red for this line. So this line is called a secant line. And notice that it is kind of poking through the graph, if you will. And so what we have in red here is the slope of that secant line, which is the average rate of change, the average rate of change between those 2 points. So that's what you've been doing for a long time in your little math career. You've been asked to find the slope between 2 points. And how do you do that? Well, you do y minus y over x minus x, right? Just like you would anything. Because you're finding the slope of this line that connects the 2 points. And that average rate of change is -1, which makes sense according to the graph because the graph is going down, and you can even go 1, 1, 1, 1. You know, you can even see that is the slope of 1. So vocabulary word, a secant line is a line that pokes through the graph, pierces the graph, if you will, and we are used to finding the average rate of change between the 2 points by just doing the slope formula between 2 points on the graph. So I've done that again. I want to change my pen to green. Looks like it's that fun green that's there. Look at that. That's a bright green, isn't it? Let's do that. So this is also a secant line, But this is a secant line that is between 3 and 1. You can kind of tell what the points are because they're in that function notation right there, and they're also at the bottom, right? And so this is a secant line between 1 and 3, 9. 1 and 3, 9. I have to go a little bit off my grid, excuse me for that, but I wanted to point a little bit farther away. And notice that if you look at this guy, this slope should be positive, right? It's going up, and we do end up with a +4. And that is the average rate of change between 1 and 3 for that function of x squared. So let me make sure I do note that. I don't think I have done that. I apologize. That this function is x squared. This function is x squared. Okay? All right. But that's what we used to do. That's back in the day. We still will do that some in this course. But our new big discovery that we want to do is what is the slope of that black line that skims the graph at 1? Okay? That's our new mystery we have to solve. And so we have, of course, a special name for that line that skims it, and the line that skims it is called the tangent line. The tangent line. So it is only tangent at x equals 1 the way it's drawn. And guys, back in geometry, you used to talk about tangent to a circle. It's that same kind of thought process. And so this line skims the parabola, like back in geometry, your line skims your circle, okay? So our big thing is, this is a tangent line, so we want to find the slope of this tangent line, the slope of the tangent line. That is the new big mystery. Woo! I know, it sounds crazy, doesn't it? So what is the slope of the tangent line? Well, I don't know exactly what it is, but I do know, because I know the slope of this green line, it is flatter than the green line, so I do know it's less than 4, right? I know that it's not like horizontal, so I know it's somewhere between 0 and 4, because if it were a flat line, it'd be 0, right? So I know that the slope of this black line is somewhere between 0 and 4. And what we're going to do is discover how to do that, but I just want us to think about what our big concept is on this, and that's find that slope. So I actually took this little graph and I tried to, it's really hard to draw slopes on this little Moby board, but I tried to show you what the tangent lines would be if I kind of drew several on the graph. So notice that this pink line, I'm trying to skim the graph. It's really hard to do that. Apologize. But notice that if I could just skim the graph, this pink line would have a negative slope, and then this green line would have a negative slope as well, but it wouldn't be as steep as this pink line. And then the red line at the vertex of the parabola would actually have a slope of 0. So let's go through that again. Pink line is negative, green line is negative but not as steep. The red line at the vertex is 0. Then the blue line is positive, and the yellow line would be positive but steeper. And so that's kind of some of the things that you need to be able to do is if you draw a line that skims the graph at a point, you need to indicate whether it has a positive slope, a negative slope, or a 0 slope. So as an introduction to all of this, I thought I'd show you kind of a lot of different tangent lines drawn. And so this is kind of how I think about it. If you could get on a really big skateboard and ride this parabola, your board would skim, like if this were the thing you're riding, your board would kind of skim the parabola, and the slope of your board at any time is that slope of that tangent line that we're in search of. You get it? So when you're down here in the gully, then your board would be horizontal and your slope would be 0. And then as you go back up the ramp or whatever over here, it would begin to be positive. So anytime someone asks you about it, you can act like you're kind of riding on a roller coaster or riding on a ski or on a skateboard, but you're skimming the graph at any point and finding what the slope of your ski or your board is at that time. Okay? I know, it's kind of crazy. So let's kind of have a little fun with it. This is x cubed, of course. Fun little x cubed. That's who he is. So, okay, this is going to probably not look real good, but we're going to try. So here we go. So I'm going to do this. Let's do something. I'm going to do green. I'm going to do a little thicker so it's a little easier to see. So, okay, here's the slope. See, I'm trying to skim. I'm trying to draw lines that skim. Skimming the graph. And I'm skimming the graph at points. I'm trying to. It's really hard to draw this. Okay, but notice that the slopes of all these little lines that get really, and they should be really close to the function at the point where I'm trying to make them be tangent, right, where it skims it. They should be really close right there. Notice that it's positive slope, then 0 slope, then positive slope. So that's one of your jobs, is to be able to look at a graph and kind of go, all right, what kind of slope do I have here? So now I'd like to show you a little thing I have called Calculus in Motion. Oh, no I don't. First of all, I want to talk to you a little bit about the different names of all of the slopes of tangent lines. So because this is such a big deal, this whole finding the slope of this tangent line, they have a lot of different names for it. And that gets confusing to people that are working with it because they're like, I don't know what you want me to do. So anytime you see slope of the tangent line, you know they want you to find that slope. If you skim the graph, what does that give you? If they ask you for the instantaneous rate of change, and let's go back and look at that picture again, the very first one. So if the red and green line are average rates of change, that's between 2 points, what this tangent line is really wanting you to find out is how fast you're going on that skateboard at the instant x equals 1. So it's an instantaneous thing, where this is an average rate, the green and red line are average rates over a period of time. What we want to know is kind of like when a policeman puts his radar on you, he's finding out how fast you're going at that instant. That's kind of what the slope of that tangent line is. It is how fast you're going or what your rate of change is at the instant of 1, okay? So they call that instantaneous rate of change. The other word that we said we'd be working with is derivative. So when I say find the derivative, I'm asking you to find the slope of the tangent line or to find that instantaneous rate of change at an instant. And then the other word we see a lot is differentiate or differentiation, and that means find the slope of the tangent line. So, you know, you'll hear me say all these words interchangeable, and so I didn't want to confuse you because I'll start using them. I know me. So I want to tell you about all these different words. They all mean find the slope of the tangent line. This is such a big deal that we have a lot of different ways that we talk about it, okay? Now it's time to go to calculus of motion and kind of give you a visual of what we're doing. All right, so here's the deal. The only way we know how to find any rates of change is to do average rates of change, and that involves 2 points. So we're going to start with that concept, and then we're going to put a little calculus magic on it. So remember, our end thing that we want to do is we want to find the slope of that tangent line at P. That is really our big deal, just like the black line that was on our original graph. You know, and look, see how that's skimming the graph right there? All right. But we can't just go directly to that because we don't know how to do that. So we're going to make a point that is H away from our point P. Okay, let me go make that. We're going to call that point Q. So we're going to like step down the number line and go up and hit a point. So if you are H away from X, then this X value that we've created is now X plus H. And if you put it into the function, no matter what it's called, then your function's height, your Y value, will be f of X plus H. Okay? So this point is X plus H, f of X plus H. And so let's draw that secant line we talked about. So the secant line is the line that goes through P and Q. Remember we talked about that a minute ago with our red and green lines. But that's not what we want. We don't want that. So what we want to explore is what would happen if I let Q get really close to P? Let me see what would happen. Look how when Q gets really close to P, the green line that is secant kind of starts looking like that black line that we really want to talk about, that tangent line. Okay? So as Q gets closer to P, the secant line becomes the tangent line. Okay? Now, what happens if Q gets closer to P? Well, we make Q by putting QH away from that X value that we had. So really what we're doing, let's see if it'll let me do this, is we're making H go to 0. See this distance of H? I am pushing it, making it smaller, so it's going to 0. So as H goes to 0, the distance between the 2 points, the secant line becomes the tangent line, and guess what? Therefore, the slope of the secant line becomes the tangent line. And what do we call the slope of the tangent line? The derivative. So this is how we say we define the derivative. And we define it by using the slope between the 2 points, f of X plus H minus f of X, that's your Y value being subtracted. And the reason that this H is down here by itself is because if you write X plus H minus X on the bottom, the X's cancel, leaving that H, okay? So it is very similar to what we did before, is that we have the function Y minus the function Y over the X's, but the some of the X parts cancel, leaving just that H. I'm going to stop and write on this at this time. This is good one to do it. Yeah. So this really should be, oh, sorry. That did not work like I planned. Let me take a picture of it. Okay. So, and then look at that. So really, what we have here, and I'm going to write this in red, is really we have f of x plus h minus f of x over x plus h minus x, right? Because that's your y's minus your x's. But if you subtract the x's, they go out, and that's why that h is by itself. Okay? All right. Let's go back and look at that now. So why is this limit there? Because that's the calculus magic. We cannot find the slope unless we have 2 points. But we really don't want the slope between the 2 points. So if we make the distance between the 2 points go to 0, then the slope of the secant line becomes the slope of the tangent line, and that's what we truly want. So if we make that distance between the 2 points kind of approach 0, then the slope of the secant line becomes the slope of the tangent line, and that is called the derivative. Okay, so really it's take a 8th grade concept, put some limit magic on it, and you've got one of the biggest parts of calculus. All right. So we're going to go now to, how about you back? Go forward. There we go. So now let's talk about how do you write a problem and ask somebody for that tangent line. And on the screen, I've kind of gone through and shown you that this is called a difference quotient because it's the difference of things and it's a fraction. And you will hear people say that, so I wanted to tell you that's what that's called. This is a difference quotient, and it's a limit of a difference quotient because your difference means subtracting and quotient means a fraction. So what we're going to do is we're going to use this one because see how the x's would go away and you just have h on the bottom. I'm going to write the definition of the derivative. Let me do something. Sorry. No CN2. All right, so the definition of the derivative, sorry, we're going to write derivative. We're going to write the derivative of f of x equals x squared. That's our guy that we started with in the beginning. Or we're going to find the slope of the tangent line, right, they all mean the same thing, slope of the tangent line of f of x equals x squared. Okay, same thing. I can ask you either one. That's what really always freaks my kids out. And they're like, wait a minute, so what does it mean to find the derivative? Oh, it's the same thing as slope of the tangent line. Yes, it is. So what I'm going to do is I'm going to actually kind of just put this into this definition. So the definition of the derivative, or the slope of the tangent line, always has the limit as h goes to 0. And what that does is it makes those 2 points that we're going to use get closer and closer together, and it makes that secant line become the tangent line. And then I'm going to put x plus h in for the x of the function. So notice I'm doing x squared. So on the top, instead of writing x squared, I'm going to write x plus h squared. And then write the function itself over h. So even though this is a limit problem, it is a very special limit problem because this limit problem is asking you for the slope of the tangent line for any x on x squared. Okay? So let's say I wanted to do this limit. Well, in the last section we did limits, we plugged in the value. So if I do that, if I plug 0 in there for h, I get x squared minus x squared, which is 0 over 0. Oh, Lordy. What do we know about 0 over 0 quotients? If you are doing a limit and you're going to a number and you plug it in and get 0 over 0, you have to factor, cancel, plug back in. But there's an answer. That's the cool thing, but there's an answer. So I'm going to expand this binomial, okay? And so, because I can't factor and cancel anything unless I actually square this. And if you square this, you get the first term squared plus 2 times the first times the last plus the last term squared. And so you must expand this in order to see what the answer is. So now I can cancel some things after I've expanded it. And notice that if I put 0 into what's left, I still get 0 over 0. So I must factor, cancel, and plug back in. So I'm going to, sorry, I'm writing with my tablet. I'm going to, there we go, factor an h out of the top. That leaves me with 2x plus h over h. And when I cancel, now plug 0 back in and I get 2x. This is called the general derivative function, okay? This is a general derivative function. Because you see how it's got an x and it's a function. So this is the derivative. It's kind of a derivative function. Because you know how we looked at different places and we said, hey, what's the derivative at x equals something? So this is a derivative for all points on x squared. So what if I wanted a particular point? Okay, let's go back and look. I'm going way back, way, way, way back. Let's go back to the beginning. So remember how I wanted to find the slope of this tangent line at x equals 1? And I said it had to be less than 4 because the slope of this guy was 4. And it had to be more than 0. Well, we just said that, let me get my pen in the right color, black. We said that if f of x is x squared, then the slope of the tangent line for f of x equals x squared is 2x. That's just what we said. Right? We just figured that out. We went through our limiting process, and we found it was 2x. So if we wanted to find out what the slope of the tangent line at x equals 1 is, we would have to plug 1 into 2x, and 2 times 1 is equal to 2. So the slope of this original tangent line that we have is 2. And does that make sense? Yep, it does. It's positive. It's less than 4, like we thought, but bigger than 0. And actually, if you do a little rise over run action on this guy, if you rise 2 and run 1, that's a point on that line. And if you fall 2 and run 1, that's a point on that line. So it really does have a slope of 2. And we found that by using our definition of our derivative, or our definition of our slope of our tangent line. Crazy? I know. What would happen if we put in, so we know, I'm going to go down a bit. So we know that the derivative, or the slope of the tangent line of, I'm going to say y, it doesn't matter, y equals x squared at x equals 1 is 2, right, because we plugged that in. What is it at x equals 0? X equals 0. Well, if you plug 0 into this derivative, 2 times 0 is 0, right? And remember, if you draw a little parabola, that's a terrible parabola, and you draw the tangent line at 0, doesn't that have a slope of 0? Yes. What would happen if we had x equals -2? If I put -2 into this derivative, I know that that is -4. Does that make sense that you would have a really steep slope? That's a terrible, let's go back to the real parabola. Let's see if we believe that would be -4 and -2. Can you bring that closer? So at -2, do you believe that would be a -4 slope? I do. I think that'd be real steep because this is -1, so this would be much steeper at -2. That tangent line right there. Tangent line right there. I do believe that would be -4. So that is just an introduction to what the big deal is. I'm going to go back to this page. So we will be asked to find the slope of the tangent line. That's the line that skims the graph. we will be asked to find the instantaneous rate of change, which is a calculus version of the average rate of change, kind of. We're going to use the average rate of change, put those points close together and find that instantaneous rate of change. People also call that the derivative, and they will ask you to differentiate or talk about the differentiation of that. So I can say that 2x is the derivative of x squared. I can say that 2x is the slope of the tangent line of x squared. I can say when I differentiate x squared, I get 2x. So all of those words mean the same thing, okay? And what's so funny is we just went back to our limit rules that we just learned, and we just had to do some expansion and factor and cancel and plug back in like we did before to find the value of the whole. And remember, this is the general derivative. If you want the derivative at a point, you have to plug that x value in, and it will tell you the slope at any point. All right, so that's the end of our derivative, introduction to derivatives. Woohoo! And next time we'll talk about, can we do this a little bit easier? Is there a little bit easier way to do this? I don't know. We'll find out on part 2 of derivatives. Thanks for being here.